So this video is going to describe drawing line and skeletal structures. Also going to talk a little bit about condensed structures. And so we talked a little bit about alkanes. Alkanes meaning uh, carbon chains that have all single bonds and that have carbons bonded with single bonds to hydrogen. So C's and H's, right? No double bonds. So think about C's and H's as caps and hats, right? So alkanes have all single bonds and they have all C's and all H's in the chain, right? These are just some simple alkanes. This is octane. This is 2,2,4-trimethylpentane, which is a constitutional isomer of octane. And then this is methane, right? This is the compound that's actually in gasoline to keep your engine from knocking, right? On the pump it says octane, but this is actually what it is. It's an isomer of octane. All right, so these are some basic alkanes. I'm going to go from 1 to 10. I'm not going to read them all. You can see methane is 1 carbon, ethane is 2 carbons, propane is 3 carbons, butane is 4, and then pentane is 5. So from pentane up to 10, it's just the Greek prefix, right? Pent meaning 5, and then you'll see on the other slide where 6 carbons is hexane, and so on and so forth. What I do want you to remember is for an alkane, you can determine the empirical formula just by this simple equation here, CnH2n plus 2, where n is the number of carbons. So for propane, if n is 3, then 2n plus 2 is equal to 8. So this is C3H8. And you can do this for any alkane. The only time it changes is when you go from an alkane to some other molecule like an alkene or an alkyl halide. Alright, so here's 6 through 10. Notice the Lewis and Lime structure. Lewis structure is the same. For hexane, Lewis and Lime basically mean the same thing. So notice here, all of your carbons are shown, all of your hydrogens are shown, right? If a carbon is not terminal, then that carbon is basically a CH2. If it's terminal, then it's a CH3. Look at the condensed form for hexane as well as for heptane. This is C7, and then here's the condensed form, and you can also write it this way where you have your CH2s combined, right? You have 5 CH2s in between the 2 N carbons, and so you just put those in parentheses and put a subscript 5 here, and that indicates that, right? Here's the question: can you draw condensed forms for octane, nonane, and decane, which is 8, 9, and 10 carbons? That's a pop quiz. It's worth 3 points. All right, so now let's talk about skeletal forms real quickly. We kind of briefly mentioned it in class, right? A skeletal form just uses simple lines to express carbon chains. Only carbon-carbon bonds or carbon R. In this case, in organic, when you see the letter R, it can be any substituent. It does not matter, right? So these only carbon-carbon bonds or CR bonds are expressed in a skeletal form. You'll see what I mean in a minute. No hydrogen bonds are shown. And what's important to remember, every terminus, meaning the end of every line, is a CH3, and every vertex is a CH2, unless otherwise noted. What I mean is, unless there's another atom other than hydrogen attached to that carbon, then it's assumed to be either a CH3 if it's at the end of a line, or a CH2 if it's where 2 lines come together. And if any other atom is attached to a vertex, then that vertex becomes a CH because I have to take an H off in order to put another atom on, right? Think about it this way: if I don't remove an H and I keep it CH2 and I bring in another substituent, then that carbon becomes or has 5 bonds to it instead of 4, right? So here's pentane. Here's the skeletal form for pentane. Here's 1 carbon. Here's another. Here's the middle carbon, and here is the outside carbon. In a skeletal form, it's okay to show the terminal carbons. Here you have a CH3 on this side and 1 on this side. It's okay to show that. All right. Here is 1, 2, 3, 4, 5, 6, 7, 8. This is octane. Notice here is the skeletal form where I start here and the skeletal form is drawn as a zigzag because we already talked about this carbon is tetrahedral. So you can start here, and this is just a 5 carbon chain. So if I start here, I'll make one stroke upward, and then I make another stroke downward, and then another stroke upward, and then another stroke downward. So if I'm drawing 8 carbons, it's always one less pencil stroke, right? So this is 7 strokes. One here, 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 and here. Right? That's just 7 strokes to give you an 8 carbon chain. It must be in a zigzag because otherwise you're basically disobeying the rules for the geometry of carbon. All right, and again, every terminus or vertex in this chain is a carbon. So these yellow dots indicate where the carbons are in this chain. All right, now it's your turn. Can you draw skeletal forms for the following Lewis structures or line structures? So here, this is a short introduction to nomenclature or naming. And we're going to just begin with alkanes, and I'm not going to go into this because we'll talk about it in a lot more depth later in the semester, but I just want to whet your appetite for it. So alkanes can be substituted if you put groups on the backbone, right? And I'll show you that in a minute. And if the groups are halogens, they're no longer alkanes, they become alkyl halides. When you hear the word alkyl, what that's referring to is any carbon chain, right? It can be 1 carbon, 2 carbons, or 10 carbons. Alkyl just means a carbon chain, and then halide obviously refers to the halogen or group 7. So chlorine, fluorine, chlorine, bromine, iodine, and astatine. All right. If the groups are carbons, then the alkanes become branched alkanes. So if the substituents on the backbone are carbon containing or alkyl groups, then the alkanes simply become branched alkanes. All right, and I just said this a second ago, I'll reiterate it. Alkyl refers to any group that contains only carbon. So it's a carbon containing group. All right, so here, this is hexane. And so real quickly, let's look at hexane. We know that this is the skeletal form, right? On the end here, this is a CH3. On this end, this is a CH3. And every one of these carbons in between are CH2s, all right? If we look at hexane here, right, we notice that there's hydrogens on this vertex, and then also hydrogens down here, and then again the terminal carbons are CH3s, and then on this end you can see the terminal carbon is also a CH3. Now when we look on this side, this is a alkyl halide because it has an alkane backbone, right? All carbons and hydrogens, and then on that backbone I have a chlorine. The name of this compound is 3-chlorohexane. All right. Right. So here's chlorine on the backbone, and then because chlorine is here, I begin counting on this end. 1, 2, 3. So this is 3-chlorohexane. Again, a branched alkane has alkyl groups attached to the backbone. So here's the backbone here, and I have a CH3, which in this case becomes a methyl group. We'll talk a lot more about that later. And this is now 3-methylhexane, right? Because the methyl or CH3 group is on carbon number 3. And I start counting from this end. 1, 2, 3. All right, let's talk a little bit about bond order. This will help you if you just remember this information going forward, because we're going to talk a lot about primary, secondary, and tertiary carbons. So carbon can be primary, it can be secondary, tertiary, or quaternary. So here again we see 3-methylhexane, right? And every carbon in the chain is shown here by a yellow dot, and then of course here's my methyl substituent. Now what do we mean by a carbon being primary, right? A primary carbon, like this one on the end here, right, is a carbon that's only bonded to one other carbon. So you can see here this carbon is bonded to the red carbon here, and so that makes this carbon a primary carbon. All right, it's bonded to this carbon here. All right. Now, in order for a carbon to be secondary, let's look at it again. So here's my carbon chain. The secondary carbon is here, and a secondary carbon is a carbon that's bonded to two other carbons. So this carbon here is bonded to this red carbon on the left, and then this red carbon on the right. And you can see in the skeletal form, this is the same carbon. It's bonded here and here. So it's bonded to two other carbons, so we call that carbon secondary. The same thing holds for tertiary. All right. The tertiary carbon is here, right? You can see that it's bonded here, here, and here to three other carbons. So let's look at it in the line structure. All right. So here's my tertiary carbon. It has a bond to a carbon here and a bond to a carbon here, as well as a bond to a carbon here. So this carbon that's circled will be considered tertiary. So carbons bonded to three other carbons are considered tertiary. This is very important that you learn this and understand how to identify these carbons now, because going forward you're going to hear primary, secondary, and tertiary. You're going to hear that many more times throughout the semester. If you have any questions, you can email, tweet, or drop by my office.